Okay, let's just dive right into this. Welcome to this explainer. Today, we're putting on our detective hats to totally dismantle one of the most stubborn, pervasive myths in machine learning right now, the myth of the universal objective. You know exactly the one I'm talking about, the idea that there's just one single magical algorithm out there that can perfectly learn the latent structure of literally any data set you throw at it. Well, today we're unpacking a fascinating new research paper that takes a completely different, honestly refreshing approach. Instead of trying to engineer yet another so-called silver bullet, the authors decided to perform a rigorous, systematic diagnostic autopsy on exactly why these models fail. It's a brilliant piece of analytical detective work, and I'm super excited to walk you through exactly what they uncovered.
To set the stage here, we really need to investigate a mystery that constantly plagues practitioners in the tech world. Why do representation learning models that look absolutely flawless on their original demonstration data just spectacularly crash and burn when handed adjacent, structurally similar datasets? I mean, it is incredibly frustrating, right? You take a model that performs flawlessly on Monday's data, you feed it Tuesday's data, which, by all accounts, looks almost completely identical, and the whole thing just falls apart. So, what's actually going on? Is it a flaw in the architecture? Is it a messed up latent space? Or is there something much deeper at play?
Now, the traditional machine learning response to a failing model is, frankly, pretty predictable. Usually, we just invent a new objective, slap a new prior onto it, and cherry-pick a nice new evaluation dataset to prove it was a success. It's this never-ending cycle. But the approach taken in this paper, it's the exact opposite. They took a highly unusual, almost brave path. They deliberately grabbed a published working framework, found exactly where it broke, and fully embraced those failures. They used them to run a meticulous, 6-phase diagnostic autopsy because they really wanted to understand the why behind the crash.
So let me introduce you to our primary subject, or victim, for today, USDF. That stands for the Universal Signal Decomposition Framework. In a nutshell, it's a variational autoencoder, so a network designed to compress and recreate data that uses a structured latent space partitioned into overlapping frequency bands. And on its original data, it works exactly as claimed. But when the researchers ran it through a custom benchmark stress test, they watched it completely fail on almost half the tasks. Out of 7 datasets, it only worked on 3. It gave intermediate results on 1, and it flat-out failed on the remaining 3. So much for a universal framework, right?
To really push USDF to its breaking point, the researchers didn't just test it on one type of data. They built an entire zoo of 7 synthetic 1D signal datasets that covered distinct structural categories. You've got multi-scale amplitude, which the model was natively built for, but then they threw in a chirp for frequency sweeps, noise color for spectral slopes, and transient location for temporally localized bursts. Then came the 3 datasets that completely broke the model. AM depth, representing envelope modulation, harmonic stack for spectral count, and waveform shape to test identity across sine, square, or triangle waves. It was the ultimate algorithm stress test.
Okay, so the failures are confirmed. Now the autopsy officially begins. Using a strict process of elimination, they interrogated the model's core components. Phase 1, let's swap the brain. They ripped out USDF's default encoder and dropped in an S5 state space layer, a much more powerful, thoroughly modern architecture, and even tested a dynamic Hebbian setup. Did it fix the failures? Nope. Okay, phase 2, swap the mouth. They brought in a heavy-hitting autoregressive GRU decoder. Still no. The model stubbornly continued to fail on AM depth, harmonic stack, and waveform shape. These failures were persisting despite major architectural overhauls.
And that brings us to the ultimate plot twist of this whole investigation. The upstream components, the encoder, the decoder, they're completely innocent. The researchers triangulated the diagnosis and realized the standard model architecture wasn't the bottleneck at all. The real culprit was the static reconstruction objective. You see, the model was being aggressively forced to perfectly recreate every single pixel or wave of the input, and that requirement violently clashed with the underlying structure of the data. Essentially, the model was being forced to memorize information that just didn't matter for certain datasets, while simultaneously discarding the crucial, class-discriminative information that actually did.
As the researchers started testing a matrix of new training objectives, this wild pattern emerged. It basically turned into a game of whack-a-mole. For instance, when they widened the model's internal information bottleneck, it fixed 2 of the failures, but left the harmonic stack dataset totally broken. So they said, okay, let's add a spectral reconstruction term. Boom! That successfully fixed the harmonic stack dataset. But here is the massive trade-off. Adding that spectral term completely broke the transient location dataset, sending its accuracy plummeting from 95% all the way down to 54%.
It was a massive game of give and take.
It's honestly just like a short blanket. If you pull it up to cover your shoulders, your feet freeze. They tried dropping reconstruction entirely and swapped to contrastive learning with universal safe augmentations. Well, that fixed two failures, but mildly degraded the noise color dataset. Then they tried a mixture of Gaussian's prior, which essentially allows the model to group data into distinct clusters. That perfectly fixed the waveform shape dataset, but it did absolutely nothing for the others. The writing on the wall was clear. There is no silver bullet. None of these inductive biases are universally better than the others. They're just completely different lenses.
So, the crucial takeaway here is that we have to stop chasing one universal objective. It doesn't exist. Instead, through this autopsy, the researchers mapped out a characterized space of 5 distinct objective recipes, with each one perfectly serving a specific structural niche. The default USDF is fantastic for band amplitude ratios. A wide bottleneck beautifully handles envelope structure. A spectral objective nails spectral counts. Contrastive learning dominates for invariance-friendly classes. And that mixture of Gaussian's prior, it handles categorically multimodal class identities. It's literally 5 distinct keys designed for 5 distinct types of locks.
But let's be practical for a second. If you get a brand new data set, how are you supposed to know which of these 5 recipes to use without burning through months of testing? Well, to solve the case, they introduced the real hero of our story, a diagnostic router. Now, this isn't some massive, computationally heavy neural network. It's actually a super simple, highly interpretable, rule-based system. It just looks at the structural signature of completely unlabeled data. We are talking about the raw signal itself, to automatically diagnose and pick the absolute best objective recipe for training.
And how exactly does it read that signature? Well, the router acts like a master key by calculating just 4 incredibly simple scalar features from the dataset shape and spectrum. First, it looks at spectral kurtosis to see if the frequency is sharp or broad. Second, it literally just counts the number of dominant peaks. Third, it checks for sudden spiky bursts using the envelope peak to RMS ratio. And finally, it measures envelope kurtosis to differentiate spiky shapes from smooth ones. By extracting just these 4 cheap fingerprints from a batch of completely unlabeled signals, the router immediately knows exactly what kind of training pressure the model requires. The results of this wildly simple routing system are absolutely staggering. Honestly, prepare to have your mind blown a little bit. By simply matching the right data fingerprint to the right objective recipe from their family of 5, this completely unlabeled router recovers a massive 95% of the performance you'd get if you had painstakingly tuned the model using perfectly labeled data. Let me just repeat that, a 95% recovery. It is completely blind to the actual labels, and yet it achieves near-perfect performance just by aligning the training objective to the structural fingerprint of the data.
When you look at the raw numbers, the performance leap is just massive. The baseline default USDF model will give you a mean accuracy of around 77% across the 7 datasets. Now, the absolute ceiling, meaning a cheating oracle that uses perfectly labeled tuning to pick the perfect recipe every single time, hits 89%. And right there in the middle is our unlabeled router at 85%. The router successfully closes 79% of the total gap between the baseline model and the perfect oracle. That is an enormous lift for a completely automated, zero-label diagnostic step.
So what's the ultimate takeaway from this explainer? It's exactly what the authors concluded in their paper. We really need to abandon the myth of unification. The idea that one objective handles every dataset is a complete trap when you are dealing with structurally diverse signals. Instead, we have to embrace the honest reality of a navigable space of objective structure alignments. We need to characterize our objectives, deeply understand their specific structural niches, and actually route our data accordingly.
As we close the case file on this really fascinating investigation, it leaves us with one highly provocative thought to ponder. We've done the autopsy, we understand the distinct structural niches, and we now have a highly effective diagnostic router that proves aligning the objective to the data is what actually drives performance. So, are we finally ready to stop searching for the silver bullet in machine learning and instead start building the right tools for the right structures? Definitely something to think about the next time your model randomly crashes on a new dataset. Thanks for hanging out with me on this explainer, and as always, keep questioning the algorithms.